All right, can you hear me now? Awesome, okay. Let me get back to sharing my screen and we should be good. Okay, cool. So today, as I mentioned, is the last day. So once again, thank you all. It's been a strange year, but it's always fun to teach. So thank you for still coming and all of that. Yeah, so as I mentioned in that email, if you guys haven't gone online to review me with the course evaluations yet, I'd really appreciate it if you did so. You should be able to find that on the recitation page. If you scroll down on like that menu that's on the left, one of the things near the bottom is the course evaluation page. And once again, I just really appreciate if you could fill that out, kind of give me some feedback for how I could change things up, make it a little better for next year. And yeah, so I also mentioned that, so today's worksheet is all going to be the new stuff. So the electrochemical battery stuff. I will by Friday post kind of a review worksheet. You should have plenty of access to other things too. Once again, for this one, it sounds like a lot of the questions he's going to be using are going to be pretty similar to the past exams. So I would definitely look at those as well as some of the new stuff that I covered today, because these obviously won't be covered on the past exams. So just a good place to look. But as long as you're comfortable with all of those things, you should be in a pretty good position for this final. And so I guess I have to do my joke first too, which is actually, we're gonna end on my favorite battery joke. I hope you appreciate it. But so Batman and Robin hop in the Batmobile. Robin tells Batman, "Oh no, the car's not starting." Batman says, "Robin, did you check the battery?" And Robin says, "What's a turry?" Because get it, they put the word bat in front of everything. There you go. Great joke, my favorite. Okay. So after that, we'll get into the actual chemistry stuff. And you guys don't have to deal with any more bad chem jokes for the rest of your life. So that's cool. But so for the following cell, basically for number one on this, I basically have a ton of follow-up questions, which should all be pretty helpful. And it's kind of different types of questions that it's asking about it. But the first part of this question is asking for you to basically draw the cell using electrochemical notation. So to do that, you'll basically have to look at the reaction and figure out which one is the cathode and which is the anode. You're going to plug it into that notation, or you have the double lines in the middle. And then you're going to have one line on each side with something filling in there. So I will give you guys a second to kind of fill that out. I don't really know how you guys can chat that to me, I guess, except for maybe tell me if lead or chromium is the, we'll say the anode. So if you could put in the chat which one is the anode, just chromium or lead, to kind of see that we're on the same page, and then see if you can practice filling in this cell notation as well. Okay, starting to get some answers in. And so basically, when you look at this cell, I don't want to spend too long on this one, just because there's not much math or anything. Looking at what's going on, basically, if you identify which is the reduction half reaction and which is the oxidation half reaction, you should be able to get a good idea of which way is which, I guess. And so looking at this cell, you have lead here, which goes from a charge of 2+ on the left to not charged on the right. And so looking at that, the lead then must be gaining electrons to cancel out that charge. So remember that reduction is gaining electrons. So lead is going to be the reduction half reaction. I'm just going to label that R. Oxidation then has to be the other one in any redox reaction. So this one here is going to be the oxidation. So this one will be the oxidation. I'll just label it with an O. And this is where, just thinking about what you know about cells, the cathode is always going to be on the right. The anode is going to be on the left. Kind of said that backwards, but, and then red cat is how you can remember that reduction happens at the cathode. So looking at that then, we just said the reduction reaction is with lead. So that means that the lead is going to be on the right side. So how you do this notation is you always put the aqueous phase closer to the two dots. So you've got lead 2 plus here, which is aqueous, and then you have the solid lead here. Then on the other side, as you guys said in the chat, everyone who responded, this one will be the anode, which is with the chromium. And so once again, you'll put the aqueous phase or the ions closer to those two lines in the middle. So you have chromium 3 plus here, and then just solid chromium to the outside. And that is the basic notation. So for part B then, it basically wants you to calculate then the standard cell potential, and then use that to figure out what delta G is of the standard cell. One thing that might come in handy for you guys is I'll give you, I guess, the half cell reactions and what their standard potential is, just because I don't want to make you guys look those up. So if you have the reaction of lead 2 plus 2 electrons goes to lead solid, E standard for that is going to equal negative 0.13 volts. And then the other half reaction, I'm not going to write it all out, but the chromium one is going to have the standard cell potential of negative 0.73 volts. And so for this type of equation, remember, so delta G standard is going to equal negative NF E standard of the cell. So you will have to calculate the standard cell potential for the cell, as well as figure out what delta G is. The hardest part for this problem is actually going to be looking at this N value here, which, remember, N in this equation represents the number of electrons that are transferred. So you will have to look back at this original reaction that's balanced and figure out how many moles of electrons are being transferred for that reaction, I guess. So that might be the trickiest part. If you guys could then chat when you get the actual delta G value, that would be perfect. But do keep in mind that you will need to figure out what that N value is, I guess. So I'll give you a few minutes to work on that. And once again, if you're stuck or don't know how to start or anything, feel free to message me privately and I can kind of point you in the right direction. I've got one right answer so far. While you guys work, I'm just gonna do a little push for my Instagram. I always do this on the last day, but if any of you guys do want to follow me, I will follow you back. It's just Matthew Gromowski on Instagram. Once again, no obligation, but just kind of fun. You can kind of see where you're at in the next few years. You can see where I'm at. And yeah, and also if you want to go to Rate My Professor, it's kind of a joke account because it's mainly friends of mine who aren't actually my students who give me some strange reviews, but if you'd like to fill out a review there, that would be pretty fun too. So feel free when you're done with this, go on either of those websites. Okay. So gotten a couple correct answers then on this problem. So what I'm gonna do is I guess just work through it. To find the standard cell potential, all you're gonna do is you basically find the difference between these two. So in this case, you're gonna have the more positive one, which will go with the cathode, minus the more negative one, which is the anode. So in this case, the standard cell potential will be minus 0.13 minus negative 0.73. So when you do that, the standard cell potential is going to equal 0.60 volts. Looking back at this reaction then, if you look at how many electrons are actually transferred, this is where, since this reaction that's drawn here is balanced, you can kind of just look at the reaction here. But since you have 3 lead 2 pluses going to 3 lead solids, you can just look at that and see that in order for each individual lead here would have to gain 2 electrons, since there's 3 of them total, that means that there's going to be 6. Looking at the chromium, there's 2 and each one has to lose 3 electrons. So once again, that's 6 electrons being transferred. So for this equation, N is going to equal 6. So all you have to do then is plug it into the equation. So delta G standard equals -6 times Faraday's constant, which is 96,485. Then you have times 0.60 volts. And I forgot the units for Faraday's constant, but it is coulombs per mole. What this value should give you then is, I'm going to make it kilojoules just to save some space, but it's 347 kilojoules. So that is it for B. For C then, basically, this is where you have to worry about the concentrations changing. And so the equation you're going to use for any of these where you see a cell potential with a given concentration or anything like that is where you have that E equals E standard minus RT over NF ln Q. And remember, Q is just going to be that reaction quotient that is associated with this reaction up here. And you don't count the solids, only the things in the aqueous phase. And for the purposes of this problem, I did forget to write that. Let's treat this as 25 degrees Celsius. And so now I'll give you a few minutes to work that out. And once again, if you have any questions, just feel free to message me. One correct answer so far. I'll give you guys about, I don't know, 30 more seconds to figure this out, and then I'll go through the answer. All right, so for this one, basically, it's pretty much just filling things into the equation as long as you figure out what Q is. Same as last problem, since you're using the same cell, E standard here is still going to be 0.6 volts. R is still just 8.314 joules per mole Kelvin. T you will have to convert into Kelvin, not Celsius, so you will have to make the 25 Celsius 298 Kelvin. N is still going to be 6, and Faraday's constant is still the same. Looking at Q then, if we go up here to the reaction, looking at it, chromium is going to be one of the products. So the concentration of chromium ions will be the products. Concentration of lead ions will be the reactants. And Q is always going to be products over reactants to their coefficient powers. And so looking at this, we basically then are going to have E equals 0.60 volts minus 8.314 joules per mole Kelvin times 298 Kelvin over 6 moles of electrons times Faraday's constant, which is 96,485 coulombs per mole of electrons. And this is going to be times the natural log. And we said earlier, I forgot to check, so chromium is going to be in the product, so that will be on top. So we have chromium. So we have 1 over 0.200. Then we have to check their coefficients. And so looking at that, chromium has a coefficient of 2, lead has a coefficient of 3. So that means we're going to put this squared and this cubed, put that all in parentheses there. I apologize for the bad handwriting again, but you should, after you plug this all into your calculator, get a value of 0.579 volts. And so believe it or not, all of these units do end up canceling out to get volts, because you end up having the Kelvin cancels here, moles of electrons cancel there. Then what do you have? Okay, so basically then you're going to end up having joules per coulomb mole electrons, which those units are the same derived units as volts. So then when you subtract that from 0.6, you're just subtracting volts. So I'll give you guys a chance to do D then, which is basically the same calculation, just with different concentrations, kind of just to compare how affecting the concentration can change the potential. So I'll give you guys a couple minutes to do that one. Once again, it should be pretty much the exact same as the previous problem. Okay, gotten a couple correct answers so far. Give another 30 seconds or so, and then should be good to move on. Okay, for those of you who are responding, it looks good so far, so that's good to see. For this one then, just gonna work it out really quick because it is kind of the exact same as the previous problem. But all you're gonna have for this one then is 0.60 volts minus 8.314 joules per mole Kelvin times 298 Kelvin over 6 moles of electrons times 96,485 coulombs per mole electron times the natural log. In this case, it's going to end up being 0.2 squared over 1.0 cubed. And this time, if you plug this all into your calculator, you should get E equals 0.614 if you round to 3 sig figs, which you should. So there you go. That's how you do these types of problems. I forgot the units here. This is volts too. But notice then that in this particular cell, when you increase the concentration of the cathode, what you're going to end up seeing is basically, or sorry, when you increase the concentration of the anode, you're going to increase the cell potential. When you increase the potential of the cathode, you're going to decrease the cell potential. And that's a trend that you'll usually see in cells. Okay, and then we only have 3 left, so it's actually possible we get done a little early today. But looking at this one, so basically what this is one of those concentration cells. And so for a concentration cell, all that means is that you don't have separate reactions in the anode and cathode. What you have is different concentrations, which actually build up that different potential. And so looking at why that kind of makes sense, I'm not positive. I think the value for the lithium cell potential, if you have that reaction, is going to be lithium plus 1 E minus goes to lithium. I think the potential is about 0.08 or something like that. So not a huge potential either way. But if you think about it, each side of the cell, so the anode and cathode, both have just lithium. So if you think about what the standard cell potential is, E standard would just be 0.08 minus 0.08, which ends up equaling 0. So there is no standard cell potential because, I mean, it kind of makes sense. There's no difference in the anode and cathode. What you do have then is a difference in concentrations. And so what you have to think about then, similar to the last equation we worked with, where E is going to equal E standard minus RT over NF ln Q. This time, the only difference between these equations is this term is actually 0. Because, as I said, when it's the same reaction happening on each side, that's going to be 0. So I forgot to label again, but we'll just assume that this is also at 25 degrees Celsius for the purposes of this problem. And then see if you can get what that ratio is. I'll give you a couple minutes to work on that. All right, and just to clarify, Q is the ratio. So whatever you get for Q when you solve for this would just be what that ratio is. I'll give you guys about 30 more seconds. All right. So for this one then, all you're basically going to do, it gave us the cell potential, which is going to be E here. It gave us a temperature, which I gave kind of later, but that's a 25 degrees Celsius. For determining the N value, when it's just a lithium to lithium plus cell, you really only have to look at the charge of the lithium ion that it's going to, which in this case is a +1 ion, which means 1 electron is transferring. So N here is also just going to equal 1. F is always going to be the same. And so basically then we have all the variables. We just need to solve for Q. So in this case, we have 0.212 volts equals negative, I'm not going to use the units for this just to save some time and space. So 8.314 times 298 over 1 mole of electrons times Faraday's constant, which is 96,485. Then it's going to be all of this times the natural log of Q. So when you solve for this, basically you're just going to end up dividing 0.212 by all of this, and then you're going to have to put e to that power, and that will give you the Q value. You should end up getting Q is a really small value of 2.609 times 10 to the minus fourth. And so basically all that means is that the ratio of reactants to products in this case, it's going to be a very small number of products to a very large number of reactants in order to make the cell have this type of potential, which kind of makes sense because once again, when you don't have any standard cell potential, you really do need that big difference in concentrations in order for anything to actually happen. All right, so then we'll move on. Just two left. These last two have to do with current and understanding what current is and how that actually works. So the key for this type of problem is remember that amps are coulombs per second. So that is the main unit for amp is a coulomb per second. I'll write that here. And I'm pretty sure there's going to be at least one question like this on the exam because Dr. Couts does really like problems like this. But no promises, I guess. I don't think he's even completely written the exam yet. But looking at this, you have then that 1 amp equals 1 coulomb per second. The other main thing that you need to know for this is the charge of 1 electron. And this is where the charge of 1 electron is 1.60 times 10 to the minus 19th coulombs. And so basically for any problem like this, you're going to have to start with either a time or a mass or whatever it basically gives you, work your way backwards through a lot of conversions, and then you can actually get to moles or mass of a certain substance. I guess for this, I should probably give you the molar mass of silver as well. Kind of left a lot out on this worksheet, I apologize. So the molar mass of silver is going to equal 107.87 grams per mole. And so then when it comes to solving these, you're basically going to do just a big railroad track that has all of the units that are going to cancel out. Do be careful that basically you will need to think about how many moles of electrons are transferring. So there will be an Avogadro's number conversion in here, but I'll give you guys a few minutes to work this one out. And then after that, we can move on to the last one, number 4. And if there's time left over, I'll just take any questions. If you want me to go over any past exams or anything, I'd be happy to do that. But if not, you guys can get out early. So I'll give you a few minutes to do this. right. So gotten 2 correct answers so far. I'll give you guys about 30 more seconds, then kind of just work through this one. All right. So basically for this, what I always look for is that it gives you a certain value that is not a conversion at all. And technically looking at this, an amp is what we're going to use as a conversion because we know an amp is a value of coulombs per second. So that's not the fixed value it gave us. The only fixed value it gave us is actually 24 hours. And so thinking about that, I'm basically just going to start the railroad tracks with 24 hours. And we have to know that the end goal of all of this is to get to what mass of silver. So we're just going to use what conversions we know to get all the way from time into a certain mass of silver. And so the first thing, since the value of amps is in coulombs per second, I'm just going to convert hours to seconds, which is 3,600 seconds is 1 hour. Now that we're in seconds, we can use the amp value it gave us. So 3.14 amps is going to be 3.14 coulombs per second. So I'm just going to plug that in here. We have 3.14 coulombs over 1 second. And this will again allows us to cancel out seconds as we go. Now that we're in coulombs, we have to think about what that actually means as far as like electrons goes. And as I gave you, the charge of 1 electron is 1.6 times 10 to the negative 19th coulombs. So I'm just going to put that in the table next. So we have 1 electron will go on top. We have 1.6 times 10 to the minus 19th electrons on the bottom, or coulombs, sorry. It's minus 19. Once again, now we can cancel out coulombs and we're in units of electrons. What you have to think about next is how many electrons are actually going to be transferring here. And so we were given, this is basically 1 electron has this charge. Since mass is always easier to work with in moles, I'm just going to convert this into moles of electrons. And to do that, I'm going to have that 1 mole of electrons is equal to 6.022 times 10 to the 23rd electrons. And this lets us cancel out the actual electrons, and now we're in moles of electrons. The next conversion is just going to be moles of electrons to moles of silver 2 plus. And for that, it's where you think about the charge of what silver is losing. And so once again, if it goes from silver 2 plus to solid silver, what that means is it's going to have to gain 2 electrons to go to a charge of 2 plus to 0. So we're just going to have that you have 2 moles of electrons. Sorry for the bad handwriting again, to 1 mole of silver 2 plus. Or just to silver. I'm going to label it as just silver. And then lastly, you just need to use that molar mass of silver. I am kind of running out of room, but the molar mass of silver, as I gave you, is going to be 107.87 grams per 1 mole silver. So looking at that, then you can cancel out moles of silver. I forgot to cancel out moles of electrons as we went. But all the units are then going to cancel out. And all you have left then is grams, which is what we were asking for. And so looking at all of this, then you plug it in your calculator. Just be very careful with parentheses and things like that, because there's a lot going on here. You'll multiply everything on top, divide by everything on the bottom, and you should get 151.861 grams. And so anytime you see one of these problems, you kind of just have to think, where are you starting? What unit conversions do you know? And plug and chug till you get to the final answer. And so number 4 here is kind of just another problem very similar to that, but kind of different. It starts with a mass and you need to work backwards for a time. So see if you can do this. And once again, it'll be a very similar problem to the previous one. Just kind of look at what units you have. You might have to work back and cancel, but it will be a little different, but I'll give you a few minutes to do that. And then I'll take any questions you guys have about anything else, and then you guys will be good to go. So as soon as I start seeing some answers for this, I'll work it out. But yeah, and let me know if you have any questions or need help getting started. If you could give me the answer in hours, that would be cool, just because I did not do this in seconds, but obviously that's technically a correct answer because I didn't specify the units. Okay. And with that, I'm just going to work it out. One key for this is to figure out what charge the gold has. And so looking at the gold chloride, or AuCl3 there, in order for the chlorides, which all have a charge of -1, in order for that to be neutrally charged, you can figure out that the gold has to have a charge of +3. So we know that gold is going to have a charge of Au +3, or 3 plus, I guess. So it's going to take 3 moles of electrons per mole of gold. We know that. Other than that, we know the current here is 0.45 amps, which once again is going to be in the units of coulombs per second. And I did forget to give you the molar mass again. I am sorry, but the molar mass of gold is going to be 196.97 grams per mole. So I apologize if that stops some of you from being able to figure that out. But basically what you're going to look at then is this time we're going to start with the mass of gold. So we have 10 grams of gold. And then that first conversion is just going to get from grams to moles. So we have 196.97 grams is 1 mole of gold. Thinking about what we're doing then, we need to get eventually to electrons so we can get to current. And we just said that it's going to take 3 moles of electrons for every part of this reaction to get from the charge of 3 plus to neutral. So we're then going to have that 1 mole of gold is going to be 3 moles of electrons. The next step then, so we're in moles of electrons. We know that the charge of 1 electron is 1.6 times 10 to the negative 19th coulombs. So all we're going to do then is convert this into just individual electrons. So we have 1 mole of electrons on the bottom. And then we have 6.022 times 10 to the 23rd electrons. The next conversion then is just going to be going from electrons to charge, which, as we said from the previous problem, the charge of 1 electron is going to be 1.6 times 10 to the negative 19th coulombs. So we're just going to do that conversion here. So 1 electron goes on the bottom. 1.60 times 10 to the minus 19th coulombs goes on top. And then lastly, you can just go from the charge. So we have 0.45 coulombs is going to be 1 second. And I do apologize for running out of room here. I need to write smaller, but it's a little hard on this. But the last conversion then that I asked for was to just get this in hours. So once again, technically, since I didn't specify units, if you just got it in seconds, that would be fine. But all you're going to do then is the last conversion So I'm just going to put that here. This does go at the end, is going to be 1 hour is 3,600 seconds. And so once again, all you're going to do is plug everything in on the top, multiply those together, divide by everything on the bottom. And I got 9.06 hours as my answer. It's very possible I did do that wrong. So I can try that math again, but I believe that is it. If not, you guys are free to go if you don't have any questions. And thank you once again for an awesome semester, even though it's kind of a weird semester, teaching you guys all online. But good luck on the final, and feel free to email me if you have any questions. And once again, if you guys could all fill out that review if you haven't yet, I'd really appreciate that. But if not, have a good summer, and hopefully see you guys around campus in the fall. Yep, I can go through the previous ones. Okay, so number one does have a lot of parts, but I'll leave this up. Let me know when you're ready and I can scroll down, or if you need me to explain any of them. Yeah. And I apologize if the work is messy. And if you have any questions on any of these, feel free to just let me know, and I would be happy to explain or do them over again. If I'm scrolling too far, just let me know and I can stop.
On B, is the answer negative or is it positive?
So for B, the answer is going to be positive. Or no, it's negative. You're right. Sorry. Yeah.
Okay.
Yep, I forgot that. Good catch.
Okay, those are the only two I needed. I came in on C, so thank
Perfect.
you.
Yeah, sure. See ya.